Part 2. This is for questions 7 to 10. Question 7, part A. Given that y is equal to the natural log of x, show that dy dx is equal to this. Now, you know that when you differentiate with respect to x the natural log of a function, then you get that function, you differentiate it, and then you divide by that same function. Okay? Now here, dy dx is going to be equal to, what we are going to have here is what is inside here. So we differentiate this, okay? But again, there is this x inside here. So differentiating a natural log of x gives you 1. That is when you differentiate the x, then you divide by that x there. Are we there? Then we are going to divide by that same function, natural log of x. So remember, this one is contained in here. So I differentiate this, which gives me 1 over x. Then I divide by that same function, just like I said here. So this therefore implies that our dy dx is going to be 1 out of, this one will multiply with this. Then we have x natural log of x, as simple as that. Then the next one, the variables x and t satisfy the differential equation. It is given that x is equal to e when t is equal to 2. Part B, solve the differential equation, obtaining an expression for x in terms of t, simplifying your answer. Now, what we are going to do here is to first separate the variables. So separating the variables, and then after we integrate. Okay, so separating the variables. And in most cases, when they give you differential equations, but they first give you the derivative here, something to differentiate, that means there is a way you are going to apply it in the next part. So let's see what happens. Now we need x on one side and then t on one side. So let us first take this on this side. We have t, then dx dt, then this one will be equal to the negative x natural log of x, and then from there we can cross multiply. When we cross multiply, you can see that this part will come down here, and then the dt would go up there. Okay, so we shall have dx, then out of x natural log of x. Okay, then this one will be equal to negative, then dt, but then you are going to divide all through by t. That is that. Then after, we are going to integrate. Okay, now we have this and then that. Now, if you are so observant, you can see that what we are having here, here is what is down here. So we are integrating 1, okay, 1 out of this. Now, by falling back here, if you integrate what is here with respect to x, and then here with respect to x, so this one will cancel out. You have your y, which is going to be equal to the integral of this. Are we there? So meaning that when we integrate what we are having up here, let me first remove that. When we integrate this, we get our y, which we have up here as the natural log of the natural log of x. You remember that? Okay, now we are going to have natural log of the natural log of x inside here. Then this one will be equal to, when we differentiate t, we get a 1 which is up here. Okay, but this one here, there is a negative 1. So if I pull out the negative here, then that means we shall get negative natural log of t, and then this one plus c. I can put the constant on the one side, and then from there we use these values here. We have x, which is equal to e, and then t is equal to 2. So what we have gotten here is what we call the general solution of the differential equation. Now, using these conditions here, we can find the value of c, and after finding the value of c, we get what we call the particular solution. So here we shall have the natural log of e. Then this one will be equal to negative. Then natural log of our t is 2. Then plus c. Now here, this one is a 1. So this is natural log of 1. Then bring this one, this side, you will get plus, then the natural log of 2, which will be c. Now that means our c is going to be the natural log of 2, because natural log of 1 is what? Is a 0. So that is that. That means the particular solution here is going to be natural log of the natural log of x. Then this one will be equal to negative natural log of t, and then plus the natural log of 2. They said we obtain an expression for x in terms of t. So we can eliminate these logarithms. Okay. How can we do this? We shall have natural log of the natural log of x. Then this one will be equal to subtraction of logarithms to the same base. What do we do to the powers? We divide them. So we have natural log of 2, then minus this. So it will be natural log of 2, then out of what? T. Are we there? Now these two logarithms are equated. That means we shall equate the powers. So this natural log of x inside here will be equal to what we are having there. So that means we have natural log of x, which will be equal to the 2 out of what? T. Then if you have log of the base is a, this is b, then it's equal to c, then that means a power c is equal to what? B. And then natural log of x is the same as saying log of base e. You see that? Right. Then this one is equal to 2 out of t. That means we shall say e power this, then it's equal to x. Is that clear? So we shall say e power, and our x here shall be equal to e power 2 out of t. As simple as that. Part C. Hence, begin from where you have stopped. State what happens to the value of x as t tends to infinity. Now remember x, we have gotten it as e to the power of 2 out of t. Now, as t tends to infinity, okay, that means this one is going to be, this part here, 2 out of t will approximate to a 0, because literally we know that 1 out of 0 is undefined. Are we there? But then if we cross multiply, we can have something like this. 1 out of infinity then will be equal to 0. So 1 divided by a very big number, you will get 0.0000000. So it is tending to a 0. You see that? Now that means our x here is going to approximate to e, then power 0, which is a 1. So x will approximate to e power 0, and then that becomes what? A 1. And that is that. Question 8 is coming from two topics here. There is integration, but again, this a is expressed in terms of a, so this means such equations cannot be solved using the usual algebraic methods. So we can use numerical solutions. You see that? So there is numerical methods here, and then also integration. The constant a is such that when you integrate from 1 to a, the natural log of x out of root of x with respect to x is equal to 6. Show that a is equal to e, then power this 1 over root of a, then plus 2. Okay? Now, here we are seeing, I can transform this one here into a product of two functions. So let this one go up here. It will become x to the power of negative a half, then the natural log of x. You see that? Now, we know that when you integrate u dv dx, here we are seeing a product of two functions, okay? So for the product of two functions, when we are integrating, for that case, we use integration by parts. So which states that when you integrate u dv dx with respect to x, this one will be equal to u, then v minus the integral of v, then du dx with respect to what? To x. Now, when you look at this one here, there is this u here, but here we are getting du dx. That means one of the functions has to be differentiated. Then this is dv dx, and then here we are seeing v. That means the other function has to be integrated. You see that? Because to get v from here, you need to integrate. Now, how do you know which function is supposed to be differentiated or integrated? I use this acronym ILET. Okay, ILET here stands for I is for inverse trigonometric functions, L logarithmic functions, A algebraic functions, T trigonometric functions, E exponential functions. Now, here we are having algebraic functions. So we have this. Then we have logarithmic functions. So this is the one here. The letter that comes before the other, that is the function you're going to differentiate. So we shall let now our u, which we are supposed to differentiate, be equal to the logarithmic function. Is that clear? So u is going to be equal to the natural log of x. Now du dx is going to be equal to 1 out of x. And then dv dx will be equal to x power negative a half. And then our v shall be the integral of x power negative a half dx. Then this one will give us, you increase the power by 1, so it will be a half, and then you divide by that new power. Then this one becomes 2, then x to the power of what? A half. Now our integration from 1 to a, x to the power of negative a half, then the natural log of x with respect to x here. This one here is going to be, what do we have? uv. What is our u? Is this one, then our v is this. So we have the natural log of x, then times 2, then x to the power of a half, minus the integral. Then our v is this 2, then x to the power of a half, then times du dx, which we are having here as 1 over x. So 1 out of x, then dx. I can put the limits here. We have a and then 1, then you equate this one to 6. Now, we can write this one first, then the natural log last, because usually students multiply this with this and then they get wrong things. So you can have 2, then x to the power of a half, and then minus, I can take this 2 outside here, then we are integrating. This is a half minus a 1, it will be x to the power of negative a half. Not so. Now, if you are so observant, you can actually see that what we are having here is what we have already done here, and the answer we got is this one here. You see that? So that means we are going to have 2, then x to the power of a half minus 2, then times 2x to the power of a half. You see? Then this one is equal to 6. Now we put the limits. So you put a first, we shall have 2, then a power half, minus, this is 4, then a power a half. Then we subtract, you put now a 1, so we shall have 2, then minus the 4. Okay, this one will be equal to 6. Now 2a power a half, 2a power a half. What do we have here? I think I forgot something here. There is a natural log. Pardon me here. There is a natural log here. After switching them, then I never wrote the natural log here of x. So it's the same thing that I'm going to do here. There's a natural log of x, and then also here we should have a natural log of a. Okay, then of course now substituting here, when you put this one here, natural log of 1 is a 0, so that one disappears. Then put a 1 here, we shall get a negative 4. Okay, so we get 2a power half, then the natural log of a minus 4a power half. Then this one is positive 4. When it crosses, it subtracts from the 6, and then we get a 2 here. Now to simplify this, I can divide all through by 2. So a to the power of a half, then natural log of a minus this will be 2, then a to the power of a half, then this one will be equal to 1. Not so? By looking at what we are having here, this is e power something. That means the a in here is the one that is made the subject. Okay? So we shall have natural log of a. This one will be equal to 1. Then take this one this side. You'll get plus. Then 2 a to the power of a half. Not so? Then we shall divide all through by a power half. So divide by a power a half. And then, of course, our a here is going to be equal to e, then power everything here. So we shall have this one, then divide by this 1 out of the square root of a, and then this one here divide by this, the a power half will disappear, then we get a 2. Not so? So we shall have this, then plus a 2, like that. And that is exactly what they have told us to show up here. Part B, verify by calculation that A lies between 9 and 11. Now, suppose this is the graph that we draw, okay, as our function, where it meets with the x-axis. That is what we call the root of the function. A root of the function is the function you substitute in the function, and then it reduces it to a 0. We also call it the 0 of a function. Then this one is going to be x. Now, if this is the root, we can also look at the x coordinates that are on the left of this root and also on the right of the root. This x coordinate here, based on what I've drawn, will give us a corresponding y coordinate, which is going to be above the x-axis, which is positive. And then this one here will give us the corresponding y coordinate, which is below the x-axis, and that one has to be a negative. This therefore implies that if the root exists between two values, when you get those two values and you substitute them in the equation of the function, then you will get two different signs. One will give a positive and then the other one will give a negative. Is that clear? Okay, so now we have our equation. We were given a, which is equal to e to the power of 1 out of root of a, then plus 2 here. So what you can do to get the function, you can bring this one this side, or you can take a the other side. You use what you want. So bringing this one this way, we shall get a, then minus e to the power of 1 out of root of a, then plus the 2, like that. Then now this one looks like e times something, so, and yet this one is a power, so we have something like that. Then this one is equal to 0. That means our function in terms of a is going to be, because it has to be a function which is equal to what? 0, such that we get the root of that function. Is that clear? So this is our function. So we have a, then minus e to the power of 1 out of the square root of a, then plus the 2 here. Now we put these two values, f of 9. So where there's a, you put a 9, then minus e to the power of, this is 1 out of root of 9, then plus the 2. We shall get a certain value, whether positive or negative. Then f of 11 will give us 11 here, minus e to the power of 1 out of root of 11, then plus the 2. This one will also give us a certain value. One positive, the other one negative. 9 minus e to the power of, this is 2 plus, then 1 out of the square root of 9. And this one here gives us negative 1.3122, negative 1.312258, and whatever is coming forth. Then how about when we put 11? So since this one is a negative, this one will be a positive. I'll come here and then I put 11. Then I also go in here and then I also put 11. So you see, this one is a positive, 1.0107. 1.0107, and the rest of the figures that come forth. Now, since there is the change of sign here, I need to conclude. Don't just leave it there. So you say, since there is change of sign, since there is a change of sign between f of 9 and f of 11, therefore you just write this statement here: A lies between 9 and 11, as simple as that. Then part C, use an iterative formula based on the equation in part A to determine A correct to 2 decimal places. Give the result of each iteration to 4 decimal places. Now we need to find the initial approximation, and I've always recommended that you use the average of the two. So let the initial approximation be, let's say it is A1, so that will be the 9 then plus 11 out of the 2. So since we have 9, 11, and then the root is in between the two, maybe it's around there, so it is better you begin from the average of these two. You draw closer to the what? The root. I don't know whether it is here or here, okay? So it is better you use the average. But even if you begin from 9 or you begin from 11 or any value that is in between there, no problem. We all get the same answer. So this one will give you a 10. Then what are we going to have next? Now to get A2, I'm going to substitute in the equation. Remember, we are having E then to the power of 1 out of root of A, which is now 10, then plus the 2 here. Then this one will be equal to what? I'll just come to this and then I take away this. Then go up here, put 10. So we get 10.1374. 10.1374. Remember they said we write our answers to 4 decimal places. Then you don't need to also show that you are substituting then E power. You don't have that time in the exam. So these other figures here, you're going to write them in, I mean, you just write those figures, okay? So maybe a 5 like that. Now, we go back to our calculator and then we put this value here. You don't go there and then you put answer, because this one is a rounded figure. So when you put this one here, it is putting that exact figure and it might fail to give you the accurate value here when it comes to iterations, okay? So just put these 4 decimal places. I'll come to this and then I will put 10.1374. This is 74, pardon me here. So we have 10.1156, 10.1156. We continue. I'll come back here. I say 10.11, then 56. And this one gives us 1190, 10.1190. And then we can continue. We come back here and then we put 1190. Then this one is 1185, 10.1185. When do you know that you're supposed to stop? That is when you get 3 consecutive values that are giving you the same value correct to 2 decimal places, okay? Now, this one here to 2 decimal places is giving us 10.12. Then here, this is 10.12. And then also here, 10.12. So we already have our answer here. So that therefore implies that we are having, these ones are giving us 10.12. So our A is therefore going to be 10.12 to 2 decimal places. And that is that. Question 9 is coming from vectors. The 2 lines L and M have these equations here, respectively. Part A, show that L and M are perpendicular. So for perpendicular lines, the scalar product of their direction vectors has to be equal to 0. So we have to get the direction vector of L, then we dot it with the direction vector of M. What do we get? So the direction vector of L is this one here, which is 4, negative 1, 3. And then the direction vector of M is this one here, which is negative 1, then 2, and then 2. Now, we multiply 4 times negative 1, that will be negative 4. Then negative 1 times 2, that will be negative 2. And then 3 times 2, that one will be a positive 6. This is negative 6, then plus the 6, we get 0. So we shall conclude, and then we say that since the scalar product of the direction vectors of the lines L and M is 0, therefore we write this statement: L and M are perpendicular. As simple as that. Then we go to the next part, the second part B, that show that L and M intersect and state the position vector of the point of intersection. Now, of course, we are going to solve these two equations simultaneously. Okay, so what is the parametric equation? So where they meet, they have the same point of intersection, meaning the x coordinate and the y coordinate and the z coordinate of this line is the same for this. Okay, now we have R here for intersection, or just write this for intersection. We equate those coordinates. So what is the parametric? We equate the parametric equations. Okay, so the x coordinate here is going to be 3, then plus 4s. So we have 3 plus 4s. This one will be equal to, the x coordinate here will be 1, then minus the t. 1 minus the t. Then we go to the y coordinate. This is 2, then minus s. 2 minus s. Then this one will be equal to, the y coordinate here is negative 1, then plus 2t. Okay, negative 1 plus 2t. And then the last one will be 5. Okay, then plus 3s. So 5 plus 3s, which is going to be equal to, then negative 2, then plus 2t. Negative 2 plus 2t. Now I can use two equations here. I solve them simultaneously. And then after that, we get our point of intersection. Okay. Let's go. So which one can we use? I think I can use these two, because when I subtract here, this t will disappear, then I remain with the s, not so? So if I get equation 2, then minus equation 3, we are going to have, let me just take this one like this, exactly. So we shall have, this one is not supposed to be there. 2 minus 5, that is a negative 3. Then negative 1 minus 3, that is a negative 4 of s. And then negative 1 minus minus 2. So this one gives us a positive 1, not so? So a positive 1, then t disappeared. Now from here, we make s the subject of the formula. I can take it this other side, and then I bring this one here. So minus 3 minus 1, then will be equal to 4s. Here it is negative 4, which is equal to 4s. That means when we divide all through by 4, s is going to be equal to negative 1. Then we can substitute in any of these two equations to get the value of t. So substituting in the first one, we shall have 2 minus, our s is a negative 1. Then this one is equal to negative 1 plus 2t. Now this one will be a 3. Then plus this one here when it crosses the equal signs. Then this one is equal to 2t. Then that means t is going to be 4 divided by 2, not so? So our t is going to be equal to 2. Now, we have used these two equations here to find the values of s and t. To show that these two lines intersect, we need to test these values using the first equation. If it is satisfied, then that means the two intersect. If it is not, then they don't intersect. And of course, when they give you a question like this and they say that show that they intersect, and indeed they have to intersect. So if you find out that they don't intersect, then check your manipulations here or your calculations. Now testing, I will say here testing with the first equation, with equation 1. Now we have 3 plus 4s is -1. Then is it equal to 1 minus your t, which you have gotten here? So here we can see that we are getting a -1. And then here 3 minus 4 will also be -1, so which is okay. Then we shall say that therefore L and M intersect. You see that? Because that equation has been satisfied. It doesn't matter which equations you use when you are solving. You can use the first and the second. You can use the second and the third like I've done. You can use the first and the third. Okay, so that is that. And since these two intersect, you are going to get the same values of S and T for whichever two equations you use. But if they don't intersect and you use this equation 1 and equation 2, the values you're going to get here are going to be different when you use the second equation and the third equation, and they might also be different when you use the first equation and the third equation. Is that clear? All right. Then next, we are supposed to state the position vector of the point of intersection. So I can say maybe our OP, the point of intersection, can be any of these two. I can use this or this one here. Choose the one you want. So it can be 3, then plus the value of S is gotten as -1. Then we have 2 minus, then -1. Then we also have, the other one is what? 5, then plus 3 of S, which is a -1. This one looks ugly. -1. So this one here will give us 3 minus 4. That one will be a -1 also. A -1. Then here we shall get a 3. And then here we shall get a 2 here. So you can write your answer like this, or you can write it in terms of I, J, and K. And then we have OP, which is equal to -I, then plus 3J, then plus 2K, like that. Part C, show that the length of the perpendicular from the origin to the line M is this one here. Now suppose I have my line M, which is going like that. Maybe this is the origin here. So we have something like that. This one is meeting this at 90 degrees. Of course, the origin here is going to be 0, 0, 0. You see that? Now, we need to find a point here on this line. Maybe it is, okay, let me use maybe point P. But since I used P before, I think it is better I can use any other later. Okay? And that is line M. So this is line M. Now, we have a point here. I need to find the equation of the line M. Okay, we have it. But then a point that lies on a straight line, its coordinates must satisfy the equation of that line. And here, F, okay, OF here is going to be the position vector of that. We use the parametric equations of this line, what? M. So we shall have 1, then minus t, 1 minus t, and then -1 plus 2t, and then we also have -2 plus 2t. These are the parametric equations of this equation, I mean the line M. Now, t can be a certain value that will now give us the f. So when you are locating the points that are lying onto that line, we shall be using different values of what? Of t. So OF is this one here. Now, O to F here, this OF here. So suppose they had given us another point, not the origin, let's say A, which has some coordinates here, then we would find the AF. Okay, now OF is that one there. In fact, I can write this one here as the coordinates of F here as 1 minus t, then negative 1 plus 2t, and then negative 2 plus 2t here. Now, since this OF is perpendicular to this line M, that means the direction vectors, when we dot them, we equate them to 1 to 0. So OF dotted to the direction vector of M, then we shall get a 0. So OF is 1 minus t, then negative 1 plus 2t, and then we have negative 2 plus 2t. This one will help us to find the value of t, and then we get the coordinates of f. Okay, the direction vector of M. Now the fact that f is on this one here, then the direction vector is around here. Those are the coefficients of t. So it is negative 1, then 2, and then 2 here. Okay, now this one here times this, you are going to get negative 1, then plus t, and then we multiply these two, we shall get negative 2, then plus 4t, and then we multiply these two, we shall get negative 4, then plus 4t, which is equal to 0. Now 4 plus 4, that is 8 plus 1, that is 9 of t, and then next we have negative 1, negative 2, that is negative 3, then minus 4, that will be negative 7. So meaning our t is going to be 7 out of 9. You see that? Then we can now substitute in here to find our OF. So our OF is therefore going to be 1 minus 7 out of 9, then negative 1 plus 2 times 7 out of 9, and then negative 2 plus 2 of 7 out of 9. You see? Now we simplify this. This is 9 minus 7. That will be 2 out of 9. Then this is negative 9 plus 14. That one will give us a positive 5 out of 9. And then this is negative 18 plus 14. That will be a negative 4 out of 9. So this is our position vector. Now we need to find, they said the length of the perpendicular from the origin. So we need to find this length here of OF. Now what do we get here? We shall get OF, its length is now going to be equal to the square root of, here we are having 2 over 9 squared, then plus 5 over 9 squared, then plus negative 4 over 9 squared. Now we are going to have, when you square the 4, I mean the 2, you are getting a 4. Then when you square the 5, you are getting 25. Then when you square 4 here, you are going to get 16. Then out of, you square the 9, it is the common denominator, that is 81. Then from here, we can see that this one will be 20. Then plus 25, that will be 45. And then here we are having root of 81. That one will give us a 9. Are we there? Then this one is the same as root of 9 times root of 5. Then down here we are having a 9. Now root of 9 is 3. Then root of 5 here. And then we are having a 9 here. So 3 goes in the 9 3 times. So we are going to get root of 5. And then out of the 3 here, and that is that. Isn't that exactly what we are having here? Yes, a third root of 5. Question 10 is coming from polynomials coupled with complex numbers. The complex number 1 plus 2i is denoted by u. The polynomial 2x cubed plus ax squared plus 4x plus b, where a and b are real constants, is denoted by p of x. It is given that u is a root of the equation p of x, which is equal to 0, part a. Find the values of a and b. That means when we get this one here and we substitute wherever there is x, then we should get a 0. Okay? Now, p of 1 plus 2i will be equal to 2 into 1 plus 2i cubed, then plus a into 1 plus 2i squared, then plus 4 into 1 plus 2i, then plus b. Okay, then from here we can get this one here, but let us first begin with this 1 plus 2i then squared. You will square 1 here, then you get a 1, then 2 times this times that will be 4i, and then we square this one here, which will be negative 4. You should know that I squared in complex numbers is always equal to negative 1. So here we are having 2 squared, then I squared. So this I squared makes this one a negative. That's why we are having a minus 4 there. Okay, then this one is going to be simplified to, now 1 minus the 4, that will be a negative 3, then plus this 4i. Then 1 plus 2i cubed is the same as 1 plus 2i squared, using rules of indices, then times 1 plus 2i, not so? Now, this one, we have already gotten it here as negative 3, then plus 4i, then times this 1 plus 2i. Whatever is in the first bracket has to multiply with whatever is in the second bracket. So we have negative 3 times 1, that will be negative 3. Then negative 3 times 2i, that will be negative 6i. Then 4i times 1, that will be 4i. And then 4i times 2i, that will be 8i squared, which will be negative 8. Then this one will be simplified to negative 3 minus 8, that will be negative 11. And then negative 6i plus 4i, that will be minus 2i. Are we there? We have 2 times this one cubed is where? Is this one here. So we shall have 2 times negative 11 minus 2i. Then plus a, then x squared is, okay, this one squared here is what? I think it is here, negative 3, then plus 4i, then plus 4, then 1 plus 2i, then plus b. This one should be equal to what? 0. Okay, when you substitute this one in here, because this one is a root, so it reduces the polynomial to 0. A root of a function is a 0 of that function. What does it mean? When you substitute that root in the function, you get a 0. So we equate this one to 0. Now we need to separate the real parts from the imaginary parts. So here we shall have 2 times negative 11. That one will be negative 22. Not so? Then we have these 3 times, a times negative 3. That will be negative 3a. And then we shall have 4 here. Then there is also this b here. We are actually adding it. Then we go to the imaginary part. We have 2 times negative 2. That will be negative 4. A times this 4. That is 4a. Then we also have 4 times the 2 here, which is 8. Okay. Then of I. You see that? Then this one will be equal to 0. But since this one is a complex number, even this way, it should be equated to a complex number. So we shall have 0, then plus 0i. Well, when we have the null complex number, 0, then it is the same as 0 plus 0i. Is that clear? All right. Now we equate the real part to the real part, then the imaginary, then to the imaginary. Okay. So we can say equating real and imaginary parts. So we have this negative 4 plus, in fact, let us simplify it. 8 here minus 4. You get a 4. So we have 4, then plus 4a. Then this one will be equal to the 0 this side. That is the imaginary part. So meaning here our 4a shall be equal to negative 4 when this one crosses the equal signs, and then dividing all through by 4, then we shall get negative 1. You see that? Then next we come to this real part. So we have negative 22 plus 4, I think that is negative 18. Then minus 3a, then plus b. This one will also be equal to the 0 here, the real part. Now we already have our a as a negative 1. So negative 18, then minus 3, then times negative 1 plus b shall be equal to 0. This is a positive 3, then minus 18, you are getting negative 15, then plus b, which is equal to 0. That means our b is going to be equal to 15, and that is that. Then next they are saying state a second complex root of this equation. Of course, when you get one of the roots being complex, then its conjugate has to also be a root. So the second complex root is the conjugate of u. So which is, now what were we given here? We were given 1 plus 2i, not so? 1 plus 2i. So you change the sign of this imaginary part to get the conjugate. So it will be 1, then minus 2i. 1 minus 2i. And that is that. Part C, find the real factors of p of x. Now, when you check back here, what we are having here is a cubic function. This cubic function, when solving it, you are expected to get 3 values. Are we there? It can maybe cross the real axis 3 times, or if you are drawing on a Cartesian plane, then the roots here. So where this one is meeting the x-axis, it is at those 3 points. Are we there? Now, since this one here is complex, and then also its complex conjugate is a root, that means this one, these two are up there, so they don't meet the x-axis. So this one has to be cutting the x-axis at only one point. You see that? So what do we do here? We are going to get a quadratic equation that is coming from these 2 roots, this one and its conjugate. Then we can use long division. We get this one here. We divide by the quadratic factor. Here we get, and then we shall get the real. So if there are 3 roots here, then they can all be real, then, or one real, and then the other 2 are complex, but these ones are conjugates. Okay? You cannot have one complex root and then the others are real. The complex roots always move in pairs, and they are conjugates of each other. Is that clear? All right. Like I said, we need to get the quadratic factor that comes from these 2 roots. Now, I want to show you how we get the quadratic equation from the roots. So if you have x, which is equal to a, maybe that is a root, and also x is equal to b, that's another root. We have already said when you are solving the quadratic equation, that can be factorized, and then you put it in the calculator and it gives you this. I've already said that you show us how you solve that quadratic equation by giving us the factors from which these roots come. So bring this one this side, you will get x minus a. Are we there? Then you also bring this one this side, you will get x minus b. Then this one is equal to 0. So it is from here that you get these values when you equate each of these factors to 0. Not so? Now let us open the brackets. When we open the brackets, then we get the quadratic equation that gives us these roots. You see that? So let us open this times this, we shall get x squared, then x times minus b, you'll get minus b of x, then minus a times the x, you'll get minus ax, and then minus a times minus b, that one gives us a positive ab. Are we there? This one is equal to 0. Now, I can factorize out the negative x, okay? That means here I will remain with a positive b because the negative is already out, and then a positive a here, and then plus the ab. I can rearrange this, then I say this is x, and then minus, this is b, or you can even write a plus b, then x, then plus ab. Now, if you look at these two, this is the sum of the two roots we have, sum of roots, and then this one here is the product of the roots. You see that? So that means we need to get the sum of the roots and then the product of the roots to get the quadratic factor. Here I will say we first find the quadratic factor, from the two complex roots. Okay, we are going to have, like I've said, here we are going to have x minus the sum of roots. You have seen that, okay? Sum of roots of x, then plus the product of roots. Then we equate this one to 0. Now we shall have x squared minus the sum of the roots. We have 1 plus 2i, then plus its conjugate is 1 minus what? 2i. Then plus the product. So we have 1 plus 2i, then times 1 minus 2i is equal to 0. When we add, of course, the imaginary part will go. Then you remain with the real part. So we have x squared, then minus 1 plus 1, we are getting a 2. So 2x here, then here plus, what do we get here when we multiply? This one is going to be the difference of two squares. So you have 1 squared, then minus the 2i squared. You see that? Then this one is equal to 0. So this one gives us x squared minus 2x. Then what does this one give us? 1. Then I squared, you know that it is always equal to negative 1. Now, so a negative, and then a negative, it becomes a positive. So you get 1 plus the 4, which gives us a 5. So we shall get plus 5, which is equal to 0. You see that? Now, we use long division to find the other real factor. So we have gotten x squared minus 2x, then plus 5. And then inside here, our polynomial is 2x cubed minus x squared, then plus the 4x, then plus the 15. Then you say this one here divide by the first one here, the rest you multiply. So here we shall get 2x, okay? Then x squared times 2x, that is 2x cubed. Then minus 2x times 2x, we shall get minus 4x squared. And then 5 times the 2x, we are getting 10x. Now when we subtract, of course, this one disappears. Then minus x squared minus 4x squared, this one will become a plus. So we have 4 minus 1, that will be a 3 also. So we shall have a 3 then of x squared here, then plus 4 minus 10, that will be a minus 6 of x. Then you drop this 15 there. Now 3x squared divide by x squared, you'll get a positive 3, not so? Then x squared times this 3, you are getting 3x squared. Then minus 2x times the 3, you are getting minus 6x. Are we there? And then 5 times 3, you are getting positive 15. Then when you subtract here, you're going to get everything going, and that is a 0. So That means the quadratic factor we got here is correct, because when you divide this one with it, you're getting a 0. Now, what are we having here? So the real factor, they even said real factors. This is just to confuse you. Are they many? It is just one. So the fact that this is cubic and this is cubic is coming from a quadratic, then times the monomial here. Okay, so what do we therefore have? The real factor here is going to be that quotient we have gotten, which is 2x plus 3, and that is that. Then part D, Roman 1, they are saying that on a sketch of an Argand diagram, shade the region whose points represent the complex number z, satisfying the inequalities z minus u less than or equal to the root of 5, and then the argument of z less than or equal to pi over 4. Now, I've already said that if you find the modulus signs on one side of the inequality or equation, then that is a circle. So here we are dealing with a circle. This is a circle of radius. The radius is what is given here, radius root of 5, and center. The center is u, which u is equal to 1 plus 2i. Okay, and I've always proved this one. If z is x plus iy, then our u is 1 plus 2i. So when I try to substitute in here, that negative is going to cancel. It's going to affect everything here like that, less than or equal to the root of 5. Now from here I can separate the real from the imaginary. So we have this, then plus y minus the 2 here, I. Then how do we get the modulus of the complex number? We get the square root of the real part, okay, squared, then plus the imaginary part, also what? Squared. You see that? And then to eliminate this square root, we square both sides. So you get x minus 1 squared, then plus y minus 2 squared, which is equal to less than or equal to, when you square here, of course, I can actually leave this one like this. Now, suppose I change this one, let's say to equals. Don't you think that this one looks exactly as this one here, which is the general equation of the circle with center AB? So center is AB. That means the center here is 1, 2, which is here is going to be 1, 2. You see that? So when you see the modular signs on one side of the inequality or equation, you should know that we are dealing with a circle, okay? But then if it is the inequality, when they say less than or equal, that means we are looking at the points that are on the circumference of this circle, because for them they are exactly r units, or the radius, which is actually root of 5. But then a point that is inside the circle, its distance here is going to be less than this radius here. So we are considering a region of points inside the circle and also on the circumference of the circle. So suppose we had less than, then that means we are only considering points that are inside the circle. So the circumference here has to be made what? Dotted, because there is no point on it that we need, okay? Because for it, the distance of that point from the center will be equal to that radius, and yet we want the distance that is less than that. You see that? All right. Now, that is that. And then this other one here, we are having a half line, okay? A half line starting, half lines start from somewhere. So starting from, since there is nothing here, because they can give you also argument for z, maybe z minus, they give you something here. That means you need to create a minus here, just like what we are having here. And then you have 1, then plus the 0i. That means that half line is going to start from which point? 1, 0. Then you draw to a certain angle. You see that? So this one is starting from 0, 0, 0, 0, okay? at an angle of this pi over 4 we are having here. Okay, so when we draw it like that, we are looking at this region of all points that are in here less than the pi over 4. So this one will be made bold because since it is less than or equal, that means also the points that are on that line are considered. But if it is, let's say, less than, then that means this one will be made dotted, meaning any point that is on this line is not considered. Okay, so that is that. Now let us draw our axes here. I've always recommended the use of a compass, okay, when it comes to drawing a circle. So better you can draw this one here. So let me put my axes here, and then also maybe the lower one here, the rear axis. So we shall have these ones labeled. Always label your axes in your sketches. So this is the rear of Z, and this is the imaginary of Z. So it is a sketch, but try to produce work that is neat. So what you can do is to bring your ruler here, and then you note these points here. Okay, you note these points here, like you mark them properly like that, such that it becomes very easy for you when you are drawing the circle. You just stretch your compass here, and then you get a perfect graph. You see that? After doing that, you also do the same up here. So I will also put my ruler here, and then we mark those points. So we have here that, then this one here, and then that one there. Now, what do we have next here? You put the markings. So we have 1. In fact, we also have 1 down here. I think I never put this one there. We need to maintain the work. The work has to be very, very systematic here. So I will put it back here, and then I will also mark at least 1 point down there. I take this one off. So this is 1, this is 2, this is 3, 4. Then we have -1, this will be 0, -1, -2, then 1, then 2, 3, then 4. Then our center is 1, 2. So I'll come to this one here. I'll need this ruler to help me locate this very well. 1, 2. So the 2 is up here. I'll put this ruler there, and then I locate 1 unit this way. So the center maybe is there. Okay, then after that, we shall get our compass, and then we draw. Now, when we are drawing, since the radius here is root of 5, okay, root of 5 is 2 point, is 2 point something. So you move, this is 1, then 2 point that, also this is 1, then 2 point that, then also up this way like that. Okay, so I'll take this root of 5 to be 2 point. I'm going to put it to, let's say, 1 decimal place. Okay, now this one will be 2 point what? Root of 5 is 2.2. I'm just going to take 2.2. Okay, now we get our compass here. So you stretch it on your compass, you get 2.2. Okay, and then you draw. So in fact, what I'm going to do here is to draw what we call the tangents. So let me duplicate this, then put it here. So this is 1 unit, then this is the second unit, then 2 point maybe 2 is somewhere there. Okay, it's the same thing we are going to have here. So 1 unit, then 2 units, and then 2 point something here, the 2.2 maybe there. Okay, then also the same thing we are going to have up here. So we have 1 unit, then 2 units. Remember, the radius is root of 5, so that is the one I'm moving. 2 units, then maybe 2.2 is up there. Okay, then we also come down here. So we have 1 unit, then 2 units, and then maybe that 2.2. 0.2 is just down there. Now, those are going to be my tangents. So when I draw, my circle has to be touching them like that, like that, like that. Then after, you remove the tangents. But then when you look at what I've drawn, it looks like a potato. You see that? So that is why I recommend the use of the compass, such that you produce something that is very perfect. Okay? So I'll get my compass here, and then I'll stretch it here. But of course, mine cannot measure this small radius here. So what I'm going to do is maybe to put it at 4 units. Then, because that one, it can go up to 3.4. So I'm going to put it at 4 units. Then I'll draw my circle. Then I diminish it. And then I see that it touches those what? Tangents. So when I diminish and then I put it here, we shall get something like that. So we shall have something like that. You can see that here it is touching here, touching here, touching here, and also there. Now we don't need these tangents. So what we shall do is to put them off just like that. So that is our circle there. Okay, then next we are going to have the half line. It is beginning from the origin here. Then you can get your protractor. Okay, you can get your protractor. You also place it here. When you place it here, then you measure the 45 degrees. So from here to here, the 45 is here. Then you can draw from the center here through that 45 there. And that is that. Then you can move your protractor. So you'll have produced something that looks very, very neat. You see that? Now for the case of shading, remember here we said that we are going to look at the region that is below the line. Okay, so we are having this one here. These are all points that are below the line. But then what do we have here? We have, it has to be inside the circle, like the way you're seeing here. So it has to be inside the circle, but then below the line. So even this part here, we shall consider it because here, a point that is here is making an angle that is a negative, which is still less than pi over 1, 4. Okay, so we shade everything. Now, I'm going to shade this clearly. So we shade something like that. Then Roman 2, find the least value of the imaginary of Z for the points in the shaded region. Give your answer in an exact form. Now, least value. Okay, how do we get that least value? Now, the lowest, if you have a circle here, like this, the lowest point of that circle has to be directly below the center here. Are we there? So you get maybe the x coordinate the y coordinate you're having there, then minus the radius. Now from our sketch here, the lowest point is this one here. So we connect this to this lowest point here. It is the one that is going to give us the what? The least value of the imaginary of Z. Okay. So how do we get that? You just get the y coordinate here. Remember, the y coordinate is this 2 here. Then you subtract the radius from there. So we can say that the least value of the imaginary of Z, is equal to the center, then minus the radius of the circle. Okay, so the center here, the imaginary part is 2i. You see that? Then minus the square root of 5. You see? But we are looking at this one. In fact, since you are just moving in this distance here, you don't need to put this I. So we shall just say 2 minus root of 5. As simple as that.